Okay, so now we shall just start. See, actually this is how it actually happens. Change in magnetic field, okay, will give you induced EMF. Okay, will give you induced EMF, and in this induced EMF will be giving you current. Okay, induced current. Okay, so now we shall proceed. Actually, this overall concept is there, right? Electromagnetic induction, that was given by the great person called as Faraday. Okay, Faraday. Okay, so the phenomenon of producing electric, okay, induced current, okay, induced current when, okay, when the magnetic, actually Faraday used coil, okay, by using coil only he produced current, but we need not to do like that. Even this method is also okay. Okay, so the phenomenon of producing induced current when the magnetic flux linked to the coil changes. Okay, so this is what the induced EMF in the coil. Okay, so this is what your first definition is. The phenomenon of producing induced current when the magnetic flux linked to the coil is what known as electromagnetic induction. Okay, is what is said to be electromagnetic induction. Okay, so now next one more thing, that is the EMF. Okay, the EMF induced in the coil so the EMF induced in the coil is called as induced EMF. See, when here current is being produced, okay, here current is being produced, right? When I just shake it, then automatically current will be produced, right? Actually, before current being created, EMF will be created, and that EMF is actually induced in this wire, so that is why that EMF is said to be induced EMF. Okay, is called as induced EMF. Okay, Then what about the induced current? The current okay, the current induced in the coil, okay, the current induced in the coil is called as, okay, is what called as induced current. Okay, so this is what your three important and basic definitions. Okay, terminologies that we want. Faraday is the person who has given this. Okay, so now we will start with our actual lesson. Okay, actually see, the first part is completely theory. It's full of theory, just like electrostatics only. Maybe I think here till now whatever we have discussed is fully theory only. That is why it's taking time. And again we have to see about some experiments also. Okay, so this one, okay, this one I can write it like this. Okay, it need not to be just magnetic field. It can be also flux. It can be also flux. There is no problem with that. Okay, so that is why I can write it like this. Okay, so flux change in the flux is directly proportional to, okay, EMF, amount of EMF produced, which is electromotive force. To produce current, EMF is required. Okay, and as you all would have guessed it, EMF is directly proportional to current. Okay, is directly proportional to current. So this is what they have written. Okay, so now till now whatever we have seen, it's all full of just concepts. Okay, some blah blah concepts only. Now we will do. And by the way, okay, by the way, this is not physics. Now what I'm going to say is not physics. I just wanted to say, okay, when I was explaining, another concept came into my brain. That is, see, this is not at all physical concept. Okay, that you cannot see it, you can only feel it, you can experience it, but you may not believe it. Okay, even the manifestation, I don't know how many of you guys have heard the terminology called as manifestation. Manifestation is also very similar to this concept. Okay, it's like, if you want something, you have to act like you already have it. If you are acting like you already have it, then anything from impossible, it will be converted to possible. Okay, it's just, that is what it is. So that is what even here you want current, and if current is there, then what will be happening? All you want is, you want current, okay, in this wire. So if current is there, then what will be happening? This wire will be moving, right? So all you have to do is, you have to behave like you already have it. So that is what, even we are making this wire to behave like already there is current. Okay, so that is why I am just shaking it. Then automatically current will start to produce in this. Okay, like when I was explaining, automatically that concept came. I don't know how many of you guys are going to believe it, or how many of you guys are going to think that I'm a boomer or a cringe fellow. I don't care, but I just said it because lots of time I've experienced it. Okay, so now 1 second. Now we shall go here. magnetic flux. Okay, so to understand this concept, okay, in this lesson we will just learn magnetic flux. I'm so sorry for the external noises. There is a railway station that is nearby my home. Well, not that close, but there is one. Okay, so okay, so magnetic flux. What is magnetic flux? We all have studied that. Magnetic flux is equal to BA cos theta. Haven't we? Well, not really magnetic flux, it can be any flux. Okay, any flux. Just remember this one thing. Okay, alright. Okay, so that flux is equal to, for example, if it is magnetic flux now, okay, you have to put here that particular field. Okay, if it is electric flux, then you have to put that particular electric field only. Okay, that field into area. Okay, that's it. You will get the magnitude. Okay, this is just way that how you can remember. Okay, so magnetic flux is equal to BA cos theta, and here it is dot product. As you all know, it is a dot product. Okay, because flux is actually, this is a scalar quantity. Okay, so this is going to be, okay, so you all know this, that it is a scalar quantity. Scalar, and these two are vector quantities. Okay, this theta, what is that theta? Actually the theta is none other than the angle that is between area vector and then magnetic field. Okay, theta is the angle between area vector and then the magnetic field. Well, I can just give you one diagram. That is, if this is what, okay, if this is what, wait, imagine this is a plate. Okay, imagine that this is a plate. I'm not even able to draw a plate. Okay, so this is your plate, and then imagine this is also your plate. Okay, now what I'm having is, I'm having magnetic field. Okay, like this, in this direction you keep it. Okay, and then also keep like this. The same plate, but just the angle is different. Okay, now I'm so sorry for this terrible diagram. I'm not a drawer. Okay, see here the angle. Okay, here the angle will be the area vector. I'm just talking about the area vector. Here the area vector will be perpendicular. Okay, to this magnetic field. Okay, and hereby the area vector will be like this, and then the magnetic field will be also like this only. Okay, magnetic field will be also like this only. So here a theta, what is a theta? Theta is the angle between the magnetic field and then the area, right? Okay, so here by it is going to be 90 degrees. So theta is equal to 90 degrees, and here by your theta is going to be, okay, 0 degrees. Okay, now we will just substitute them in the formula, that is flux is equal to BA cos 0 degrees, and hereby flux is equal to BA 90 degrees. Okay, so BA 90 degrees. Now here you can very easily say that, okay, so what is it? It is an even function. Cos is an even function. So for even function, here you will be getting 1. Okay, so BA. Here you will be getting maximum flux. Okay, here you will be getting maximum flux. Okay, here you will be getting maximum flux, and then hereby you will be getting minimum flux. So flux minimum is going to be here. What is it? It is cos 90 now. Okay, so cos 90 degrees, which is equal to 0. Okay, so whenever the angle between magnetic, so, and also you can keep it like this. Okay, and then also very important relationship, that is which color? This color. That is flux is inversely proportional to theta. Okay, so flux is inversely proportional to theta. That's it. Okay, so here is theta, is this. One second. So just we all shall keep it as 90 to 70. So theta, okay, so theta should be because if you just take theta more than more than 360, there is possible, but if you are taking it now, then it will increase now. So that is why I kept it as 270. You just see the graph of cos theta like this one, you guess, right? So from here to here it is decreasing, it is 90. Okay, it is decreasing. From here to here also it is decreasing. In applications of derivatives, increasing, decreasing, we have studied, right? That same thing only. Okay, here to here also it is strictly, from here to here it is strictly decreasing, which is what is this? So this is 90, this is 180. Okay, so sorry, this is 180, this is 180. Wait a second. 0, then 90, then again 180, yeah, this is 180. But from here it starts to increase. Okay, but here from here it starts to it starts to do what? It starts to increase. Nah, so I cannot give that. So that is why the domain is 0 to 180 degrees. Okay, so this is what the first part. Now we shall go with some experiments, and also these experiments are, and also please practice one or two sums, because this is a place where many of us do some mistakes. Okay, so now again we are going into some theory by experiments. You are totally having 3 different experiments. Okay, so you are having how many? 3 different experiments. So what are they? First experiment. Okay, then the second experiment. Okay, then the third experiment. Okay, so all these 3 experiments are very simple and very easy. So first experiment is first experiment and then second experiment are literally same only. There isn't that much of difference. I will say, okay, what is the first experiment? Here you are having a coil. Okay, so this is what that coil is. Okay, So hereby I'm having a galvanometer, and then current is flowing like this, and then there is deflection in galvanometer. We all know that all those I is directly proportional to the theta in the galvanometer, everything we know. Now what I'm having is I'm having a magnet. So yeah, the current direction is all dependent. So current direction is all dependent on this direction. See, really believe me, in this, in the electrostatics also, the theory wasn't that much confusing, even in electrostatics questions will not be asked in theory, but here some questions are like that. Theory part is where I personally feel like, why is this given? Why is this theory? But concepts are very easy, derivations are very easy, but theory is kind of like this only. Now hereby it is solved. So the direction of the current is like this. And then wait, I will explain what is it. See, it's actually very simple, First of all, there is a bar magnet. This is with the coil. Here there is a galvanometer. Galvanometer is what? Here it is used to measure is there current or not. Ammeter is used to measure the current. Galvanometer or the voltmeter is used to measure the voltage. So here it is just brought in and out. It was just brought in and out, and in that time there was a deflection in the galvanometer. And if there is deflection in the galvanometer, then there is V, and if there is V, then there is I. That's it. Very easy. So yeah. Now hereby I'm having another thing. So this is what we have. Wait a second. Select. This is what your first experiment. Now this time what happens is actually so the flux over here. So C2 is there. See, this is coil 1. This is C is actually the representation of coil, and then this is also another coil. See, here is one coil, and here is also another coil. Now this coil is there, right? And this coil is actually the thing that is having. This is the coil that is actually having current in it. As you can see here, it is having battery. And this coil doesn't have anything like that. Now, when you just take this thing, when you just wait, what was it shaking? So they were just shaking it, they were just bringing it closer, and then they were just shaking it, then automatically there is change in the magnetic flux. See, magnetic field, there should be a disturbance in the magnetic field. For an example, if here is a magnetic field, and if there is a coil over here, then this coil should rotate. It should just rotate. That's it. This coil should be rotating. So then automatically there will be a disturbance in the magnetic field. Now automatically you can just see, you can just see that there is deflection in the galvanometer, then there will be current also. So this is your next thing. Now again, very similar thing, but this time they have gone in an advanced level. It wasn't just this this simple. And also, do you know why? Why is this happening? How is this happening? Actually, we all know that a coil will be also acting like a bar magnet only. So here, this is very similar, isn't it? With this, I already said in the previous lessons itself. In the previous lessons, even we have discussed. So but I will just write it. So that is bar magnet and then coil, okay, and then a coil. Will be actually acting in the same way. Okay, so now for the second time, what happened is, now what they did is, actually it is very simple. Here I have given you one relationship, right? That is, change in the magnetic flux is directly proportional to current. That is also okay. You can just exclude this, hide this, and then you will get this. Okay, change in magnetic flux is directly proportional to current. Now, in an experimental way, they are saying that. Okay, how it is possible? It is very simple. Here, it is a tap key. Okay, if in case this is what known as tap key. Here you can see this. It is actually tap key. Or you can very well, okay, watch it. Here this is a tap key. Whenever this is actually in opened position, if it is closed position, it will be like this. Okay, so whenever this position is open, then the current flow will not be there, or it will be very, very minimum. Okay, so because of that, actually tap key should be placed in the other side. Okay, tap key should be placed in the other side. So which means I've drawn that wrongly. Now you just check. Okay, oh god. Okay, so now you just check. Now you all can see it in a very clear way. Okay, so when it is closed, okay, then in that time current will be produced in a lot. It is conventional current now. Okay, so because of this, now current will be there. Okay, magnetic, and here also current will be there. And when they checked, okay, if current flow over here is less, now then the current flow over here is also less, because the deflection in the galvanometer is less. And if current flow over here is high, then here also it is high, because the deflection in the galvanometer over here is high. That's the reason. Okay, so now I'm just going to say a condition, that is, okay, see, this is what we are going to see. And also you have to know this. Okay, you have to know this. There will be mutual induction, there will be self-induction. What is self-induction? Over here what is happening is, okay, self-induction. Okay, we will talk about self-induction in the future. Now we will go to Faraday's laws. Okay. Okay, so Faraday's law of EMF. Laws of EMI. Okay, so the first law. Okay, so the first law is actually very simple law. Okay, the law states that whenever there is change in the magnetic flux, EMF is produced. EMF produced lasts so long as change in magnetic flux is continuous. Okay, so what does it mean? First, I'll just write it. Whenever there is a change in magnetic flux, okay, in magnetic flux, EMF is produced. Okay, EMF lasts so long as the change, okay, in magnetic flux is continuous. So what does it mean? It means that, see, whenever there is a change in the magnetic field, if there is a change in the magnetic flux or in the magnetic field, then automatically EMF will be produced. Okay, and then this EMF will be lasting. Okay, this EMF will be in that conductor as long as there is change in the magnetic flux. If this change in magnetic flux stops now, then automatically EMF will also stop. Okay, so that is what they are saying. So this is what your first law is saying. It is all about duration. It's all about duration. Okay, so now next law is your second law. Okay. Your second law is actually very simple. It is all just like Newton's second law. Okay, it is like Newton's second law. It is like E is directly. What is E? E is your EMF. Okay, each and every time instead of writing EMF, already electromotive forces short form is what EMF. Even that I'm feeling lazy, so we are writing it as E. Okay, so E is directly proportional to d phi by dt. Okay, d phi by dt. Well, you might think like, isn't this the thing that was given even in this first law? Okay, well, actually it is saying that EMF will be produced as long as there is change in the magnetic flux. But here it is said that if in case the change in the magnetic flux is high, then automatically EMF will be also high. That is what here they are saying. Okay, and also you can see that it is a differentiability. It is a differential equation. Okay, but the thing is, here is a drawback. Okay, here is a drawback. They did not say in which direction EMF will be produced. They said that EMF will be produced, but in which direction EMF will be produced, that they didn't give us. Now that is what third law. Okay, which is Lenz's law. Okay, which is Lenz's law. Third. Okay, well, this was given by Lenz. Okay, he is also a scientist. Lenz's law. Okay, by the way, please do not confuse that Lenz's law with this Lenz's law. In what is that lesson? Optics. Okay, in ray optics, we will be studying Lenz's law, which is, what is that law? Oh God. So Lenz's law is actually P is equal to 1 by F, which is equal to mu minus 1 into 1 by R1 minus 1 by R2. This is something that we will study in there. Okay, P is equal to 1 by F, which is equal to mu minus 1 into 1 by R1 minus 1 by R2. This is something that we will be studying in ray optics. Okay, not here, in ray optics. Okay, very important formula by the way. Okay, but here we will not study this. We will just study the further, okay, a further process of this equation itself. Okay, just another step of this equation we are going to study. And by the way, this Lenz's law was actually a topic that was said to me by my friend to study when I was in 10th standard. Okay. There is scratches. There are lots of scratches on board. Everything is done by my little finger. Okay. So you will come back here, here itself. That is, see, Lenz's law. I don't know how many of you guys are reading newspaper. I don't read newspaper, but my grandmother does, and she'll be giving me some bits of the information. Over there, it was this same thing. The sentence that I'm going to give was there. Okay, Valartha kida marble payum. Okay, Valartha kida marble payum. This is in a Tamil. This is a Tamil palamoli. Okay, it is a say in Tamil. That is Valartha kida marble payum, which means you will be growing something with love, with care, with affection, with compassion, with concern. Everything will be growing something. Okay, but at last that thing will be backstabbing you. Kattappa. Okay, that thing only over here also is happening. The current. Okay, see, the magnetic field is the thing that is primarily responsible. Okay, for this. But the EMF produced will be opposite to the direction of the current. Okay, I know nothing makes sense. We will just go into it. Okay, we will just go into it. Okay, by the way, the drawback or the outlag was that they didn't give you the direction of EMF. Okay, but there is no direction of EMF. No direction of EMF. Okay, now coming back to Lenz's law itself, that is E is equal to minus d phi by dt. Okay, E is equal to so E is equal to minus d phi by dt. It is actually this law is actually the sentence is actually the induced EMF EMF always flows in such a direction, that it opposes APPO. Okay. Sometimes whenever I stand long for a day, actually this is my 4th video of the day. 4 hours I'm standing, which is such a great record for me. Okay, opposes the change or the cause that produces it, or the cause that produces it. Okay, just 1 second. Okay, so to understand this is a very easy concept. For an example, this is your coil. Okay, so for an example, this is your coil. Now there is a bar magnet. Okay, so for an example, this is North Pole. Okay, this is North Pole. Now this there will be, okay, now this is moving here and there, okay, it is just moving like this. Then that means what? There is change in the magnetic flux. Then automatically there will be current that will be induced over here. And we all know whenever current is produced, magnetic field will be produced. And here, since to oppose it, to oppose this magnet, okay, to oppose this magnet, here current will be produced. And that current will be producing again north pole only. So that this will be opposing this, so that it will not come in. Okay, so that it will not come in. Now the question is actually the current direction. Okay, the direction of the current determines whether here north pole should be produced or south pole should be produced. Okay, or also when it is moving like this, okay, then here in that time south pole will be produced. Okay, south pole will be produced to attract it. Okay, whatever you do, it will be opposing it. If you are trying to go away now, it will not leave you. If you are trying to go inside now, it will not leave you. Or even if in case you just tilt it like this, so then over in that condition, here there will be south pole, here there will be north pole. Okay, same thing. Whenever it is going like this, north pole will be produced, so that it will attract. And whenever you are going like this, then south pole will be produced, so that it will repel. Okay, now the direction of this current is the thing that is that has this main responsibility, whether it can attract or whether it can repel. Okay, that we shall check. Do you know how to check it? That rule is called as end rule. And by the way, how did it come? Very simple. Here it is a proportionality symbol, right? Okay, to remove proportionality, what you have to do is you have to replace it by equal to and a constant. And here that constant is -1. That is how we have got it from here to here. Okay. Now end rule. What is end rule? End rule is actually very simple. For an example, you are having, okay, a circuit. Okay, and here you are having a magnet. Hare Rama. Okay, so the end rule, for an example, here you are having north pole, here you are having south pole, here you are having south pole, here you are having north pole. Okay, now you are bringing this here in this direction. Okay, in this direction you are just taking it. Okay, then what will be happening is here it will be actually rotating like this. Okay, correct? I'm very weak in diagrams like this. Okay, so it will be like this. Okay, what is this? This is clockwise and anti-clockwise. That I don't know whether it's this clockwise or anti-clockwise. So this is anti-clockwise. Okay, so this is anti-clockwise. Actually, my grandmother taught me. See, some in this clockwise, anti-clockwise, they always get confused. I don't know why, but I cannot remember how clock rotates. I have to draw the diagram. So what my grandmother said, just to put this structure. She said this is clockwise. I know that is very simple, but some people will have some basic problems. Not like that. I have this one. Okay, and also here it will be like this, in this direction, which is clockwise. This opposite, right? So hereby it is going to be like this. Okay, pakka, done, right? And here also it is going like this direction only, and the same current will be produced. The same current will be produced when here south is there, here north is there, and then this is trying to leave this side. Okay, and here also north, south, okay, like this it will be produced. So this is what your end rule is, and based on this end rule and this one you can very easily do lots of sum. And the last step, that is not the least step, okay, so which is going to be for this is actually for only one loop, loop in sense this is one loop, okay, for n number of loops, not then loops like this, okay. So for n number of loops, for n loops, over there it's very simple, that is E is equal to minus n d phi by dt. By the way, what is everyone who would have seen my differentiability and differentiation videos, and as well as applications of derivatives, okay, they would have known what does it mean. This means this is equal to minus n into phi 2 minus phi 1 whole divided by, okay, so whole divided by T2, okay, and also no problem if you write the exact opposite. This is also equal to this one. This also I said very clearly. This is phi 1 minus 1 minus phi 2 T1 minus T2. This is also okay. Minus you take common, the same thing only will be getting now. So then what's the problem? Okay, so that's it for today's video. We'll be meeting in another amazing video. Till then, bye bye.